The meaning of this word interrupt is to break the sequence of operation. We can more clearly understand its meaning by taking an example that suppose we are doing our homework in our room and suddenly our mother and father come into the room and they told us that just do this work for me and then you can do your studies. So what we do, we finishes what we are reading, means if we are reading a sentence, we complete that sentence and then we do the work for our mother and father, and then again we come to our seat and then we again resumes our studies. So what is this? The sequence of our studies is broken. We have done a work given to us by our mother and father, and then again we are completing our studies. So if we take, this is a kind of interrupt. So interrupt, the word interrupt means to break the sequence of operation. Now, if we talk about the interrupts in case of microprocessors, then while the microprocessor, they are executing a program, they execute instructions one by one, means in a sequence they are going to execute the instructions. Now, while executing the instructions, if an interrupt occurs, then what the microprocessor do? The microprocessor finishes the execution of the current instruction, then it jumps to some other location where a short program which is known as the interrupt service routine is written. It is going to execute that interrupt service routine and then it is again going to come back at the main program and then resume the execution of the remaining instructions. So this is an interrupt in the case of microprocessors. So while the CPU, that is the microprocessor, it is executing a program, an interrupt breaks the normal execution of instructions and diverts its execution to some other program which is called the interrupt service routine, that is ISR. This ISR is also a short program in which some instructions are written, so those instructions will be executed. And after executing the interrupt service routine, the control is transferred again back to the main program. So for every interrupt, we have an interrupt service routine which is written at some other memory location. And whenever an interrupt is given to the microprocessor finishes the execution of the current instruction, then it jumps to that memory location where the interrupt service routine is written. It is going to execute the interrupt service routine and again it is going to come back to the main program to execute the remaining instructions. So that is how whenever an interrupt is given to the microprocessor, it works. Okay. Now, why there is a need for an interrupt? This interrupt is provided to the microprocessor by the interfacing devices or the input output devices which want to communicate with the microprocessor. Now these peripheral devices or the input output devices, maybe it happens that their speed is very slow as compared to the speed of processing of the microprocessor. Means at the speed at which they are transferring the data or receiving the data, that is very slow as compared to the 8086 microprocessor. So to synchronize the working of the microprocessors and the peripheral or the interfacing devices, the interrupt is given to the microprocessor by the peripheral devices. So that is why there is a need for an interrupt, so that if the interfacing devices which are working at a very low transfer rate, they can also communicate with the microprocessor. So the need of interrupt arises whenever the microprocessor, it is interfaced with the input output devices which are providing or require, means which are transmitting or receiving the data at relatively low data transfer rate. So in that case, interrupts is required. Okay. Now let's come to the type of interrupts in the 8086 microprocessor. In 8086 microprocessor, there are two types of interrupts. One is the hardware interrupt and second type it is the software interrupts. Now the hardware interrupts, they are also classified into two categories, maskable and non-maskable. So if we see the characterization of the interrupts, then interrupts in 8086, they are classified into two categories, hardware and software. Now hardware interrupts, they are also classified. So let's see the chart for this, that if we have the interrupts, they are classified into two categories, hardware interrupt and software interrupt. Hardware interrupts, they are further divided into maskable and non-maskable. So this is the classification or the types of interrupts in the 8086 microprocessor. So let us study these types of interrupts in detail. First, we will start with the hardware interrupts. Hardware interrupts, as the name says, that these interrupts are provided by some hardware circuitry. Okay, so the peripheral devices or the interfacing devices, they are going to provide this interrupt to the microprocessor through some hardware. So here these interrupts are caused by sending a signal through a specified pin to the microprocessor. The microprocessor IC, it will have various pins, so some pin will be associated with that interrupt. So interfacing devices or the peripheral devices, they are going to send a signal through that pin to the microprocessor. So some hardware is involved in this interrupt, so that is why these type of interrupts are known as the hardware interrupts. So I have written here that these interrupts are caused by any peripheral devices by sending a signal through a specified pin to the microprocessor. So here if we have the microprocessor and it is the peripheral device, or we can say the input output device, this is our microprocessor. So some pin will be there, and this input output devices, it is going to send a signal to this pin, and through this pin the microprocessor will be interrupted. Okay. Now coming to the 8086 microprocessor, there are two hardware interrupts which are known as the NMI and the INTR. It has two hardware interrupts. First is NMI and second is INTR. These interrupts are given at particular pins of the 8086 IC. The full form of these interrupts is non-maskable interrupt and interrupt request. As the hardware interrupts, they are further classified into maskable and non-maskable interrupts. So among these two interrupts of the 8086, the NMI, it is a non-maskable interrupt, and INTR, it is a maskable interrupt. Non-maskable and maskable interrupts means that suppose this interrupt is given by the peripheral device to the microprocessor. So microprocessor has to, at any cost, it has to execute or access this NMI, that is non-maskable interrupt. It cannot avoid this interrupt. It has to execute the non-maskable interrupt. Whereas the maskable interrupts, they can be masked for some time, means that their execution can be delayed by the microprocessor for some time. Okay, so maskable interrupts that can be masked for some time, and non-maskable interrupts which cannot be masked, and the microprocessor has to execute those instructions. It has to give the highest priority to them. Okay, so among these two interrupts, NMI and INTR, it is the non-maskable, and INTR, it is the maskable interrupt. So NMI, it is going to have the highest priority, and INTR, it is having the lowest priority. So if these two signals are simultaneously given to the microprocessor, then first the interrupt which is having the highest priority, that will be executed, and after that the interrupt which is having the lower priority, then that will be executed. Now these were the two hardware interrupts. Apart from these two, there is also one interrupt acknowledge signal in the 8086 which is known as INTA. This is also an interrupt pin, but this is an acknowledgement signal. Means whenever an interrupt request, that is INTR, is given to the microprocessor is going to generate a signal which is known as the interrupt acknowledge signal, and this signal will indicate the peripheral devices that the request of interrupt which they have given to the processor, it is being accepted and it has been received by the microprocessor. So this will be an acknowledgement signal of the interrupt request. So if we talk about the hardware interrupts, we will have the two hardware interrupts, NMI and INTR, and also one hardware pin which is known as INTA, which is the interrupt acknowledge pin. So these are the hardware interrupts. Okay. Now we are going to study these interrupts in detail. First we will start with the NMI, that is non-maskable interrupt. This NMI, it is a hardware interrupt, and it is the single one non-maskable interrupt in the 8086 microprocessor. This interrupt has the highest priority among all the interrupts, and also it is the type 2 interrupt. Now, when this interrupt is given to the microprocessor, then what are the actions which are performed by the microprocessor. First, the microprocessor, because whenever an interrupt is given to the microprocessor, what it does, it completes the execution of the current instruction. So in microprocessor, there is a pointer. In 8086, there is a pointer which is known as the instruction pointer, which points to the memory location which is having the next instruction which is to be executed. So suppose that some instructions are written, and currently the 8086 it is executing this instruction. Now when this is executing this instruction and interrupt occurs, so it is going to some other location where the interrupt service routine is written. So the microprocessor, if it jumps from this location to the ISR location, so when it comes back, then it has to know that the next instruction it is written at this memory location. So to store the address where the next instruction is written, we have the instruction pointer which always keep tracks where the next instruction which is to be executed is stored. So this instruction pointer contents, they have to be stored at some location, so that when the microprocessor returns back, it get to know from the contents that here the next instruction is written and I have to resume from this position. Okay, so let's see that what actions takes place when this NMI interrupt is given to the microprocessor. So first, the microprocessor, it completes the current instruction that is in progress. So suppose like here an instruction is written like move AX comma BX. So this instruction is the what the microprocessor is currently executing. So microprocessor, it will first complete the current instruction that is in progress. Next, suppose when the microprocessor is executing the program, the flag register has been affected, like the various flags, sign flag, parity flag, carry flag. If any of the flag is reset or set during the execution of the program, so that status of the flag register, it has to be stored at some location, so that when the microprocessor resumes the program execution, it get to know that that is the status of the flag register. So the flag register contents, they are pushed onto the stack. Stack, it is a temporary memory location which is used to store the intermediate results or intermediate values. So whenever we want to store some temporary data, that will be stored in the stack. So the status of the flag register, that will be stored in the stack. Pushes means we use the two instruction push and pop. So push is used to store some data in the stack, and pop is used to get out some data from the stack. So here we are storing the status of the flag register into the stack. That is why it is written that pushes the flag register values onto the stack. So we are going to use the push instruction here. Now, as I have told that microprocessor should know that where the next instruction which it has to execute, it is written. So the address of that next instruction, it is stored in the instruction pointer. So addresses in the 8086 microprocessor, it consists of two contents. One, it is the segment address, and second is the offset address. So segment address is the address of the four segments like code segment, data segment, stack segment. Okay, now here we have the instructions, they are always stored in the code segment. So the address here of the program, it will consist of the code segment address plus the offset address. Offset address means the address which is in the instruction pointer. So now next step will be to push the code segment values and the instruction pointer values of the return address, means the address where the next instruction is written, that is return address, onto the stack. So first the flag register contents will be pushed, then the code segment address and the instruction pointer address will be pushed onto the stack. So all the status of that current program, that will be stored in the stack, so that when the microprocessor resumes it resumes to its main program, it get to collect all the values. Okay, it is just like that when we are reading a book and suddenly someone interrupts us. So what we put a bookmark there, so that we will get to know that we have to resume our reading from that page. So that bookmark is here, the stack. We are using the stack to store all the values, so that when the microprocessor resumes to the main program, it can collect all the values from the stack. Okay. Now the program, the microprocessor, it has to jump to that memory location where the interrupt service routine is written. Okay, so the instruction pointer contents, they are already stored in stack. Now instruction pointer, it is going to point to the memory location where the interrupt service routine is written. Now for NMI, that is the non-maskable interrupt, the interrupt service routine is written at the memory location 0008H. Okay, so the instruction pointer, it is loaded with the contents now. Addresses, as I have told that in 8086, the addresses, they consist of, first is the segment address plus the offset address. So in this case, 00008, the segment address is what? It is 0000H. Okay, and offset address is what? It is 0008H. Okay, so when these two are added, the segment address, it has to be multiplied with 10H. It has to be, we have to add 0H in it, and then it is added to the offset address to get the physical address. So this is how the address is generated in 8086. So for the NMI, we have the offset address as 0008 and the segment address is 000H. So the address where the ISR is written, this address comes out to be 00008H. Okay, H denotes that this notation, it is in hexadecimal. Okay, now next step will be now instruction pointer, means that where the instruction which is to be executed, that is written. So first instruction will be written at 00008. Next instruction will be written at two places after it, so that address will be 0000AH. So code segment register, it is loaded from the contents of the next word location. And we have two flags, interrupt flag and trap flag. These flags are reset to 0. So these are the actions which are taken by the microprocessor when the non-maskable interrupt NMI is given to it. Okay. First, the microprocessor, it is going to complete the execution of the current instruction. Then it is going to push the contents of the flag register onto the stack. Then it is going to push the contents of the instruction pointer and code segment onto the stack. Then it is going to load the instruction pointer with the address 00008, so that the microprocessor microprocessor can jump to this location and can execute the interrupt service routine. The code segment register, it will be loaded with the contents of the next word location, which is written after 2 bytes from this location. Okay, then interrupt flag and the trap flag, they are set to 0. So these are the actions which occur when NMI interrupt is given. Next we have the interrupt INTR. So next hardware interrupt we have is the interrupt request. This is a maskable hardware interrupt. Maskable because the microprocessor, it can enable or disable this interrupt. Means it can be set or reset by the microprocessor. That is why it is a maskable interrupt. And it is having lower priority than the non-maskable interrupt NMI. So INTR, it is the maskable interrupt, and the microprocessor can enable or disable this interrupt by using the two instructions, set interrupt flag and clear interrupt flag. So through set interrupt flag, that is STI, we can use this instruction to set the interrupt flag, means to make the interrupt flag value equal to 1. And also we can disable this interrupt by using the clear interrupt flag CLI, which can reset this interrupt flag, going to clear it, means it is going to make its value equal to 0. So we can set or reset this interrupt flag register, through which we can enable and disable this interrupt INTR. Okay. This interrupt request signal, it is activated by an input output port, means an input output port will be connected to an input output devices. So that port is going to produce this signal. It is going to give that request to the microprocessor. Now, when this interrupt is enabled and the non-maskable interrupt, that is NMI, that is disabled, because if both these interrupts are given and NMI is having higher priority, so first NMI will be executed. So NMI has to be disabled if this INTR has to be executed. Okay. So if INTR is enabled and NMI is disabled, then what this microprocessor will do, it is giving it is having that interrupt request. So microprocessor, it is going to complete the execution of the current instruction, and it is going to produce it is going to send a number 0 twice on the INTA pin. So when INTR interrupt is generated, then microprocessor, it completes the execution of current instruction, then it sends 0 on the INTA pin twice. Okay, so the first 0, it indicates the peripheral device which is sending the interrupt request, that the microprocessor, it is ready, get ready, so that the microprocessor can communicate to it, or it can transfer the data to the peripheral device. So first 0 indicates the peripheral device to get ready, and second 0, it wants the some number, that is the type of the interrupt which is given to the microprocessor. That type number will be provided by a programmable interrupt controller. So if we have this 0 is sent twice, so first 0, it informs the external device to get ready, and second 0, microprocessor receives the 8-bit type number of interrupt. Suppose this is X. So the type of interrupt will be provided by the microprocessor by from the programmable interrupt controller, that is PIC. So that controller, it is going to provide the microprocessor the type of the interrupt, so that the microprocessor will get to know that this type of interrupt is generated. Okay. Now again, if we come to the actions which are performed by the microprocessor when this INTR request is given, then first it is going to complete the current execution. So first the current instruction will be completed, then the microprocessor, it is going to activate the interrupt acknowledge output, means it is going to inform the external device that it has received the interrupt request and get ready for the transfer of data. Okay, and then it is going to receive the interrupt type from the interrupt controller. Say that the type of interrupt means it is X. It is denoted by, let it is denoted by X. Now the flag register, the code segment value and the instruction pointer values, all those values are again pushed onto the stack, so that when the microprocessor resumes to the main program, it can get all those values from the stack. Now microprocessor has to jump to the location where interrupt service routine is written. So for INTR, so the instruction pointer that will be loaded with the address where the interrupt service routine is written. So for this INTR, the that address where the interrupt service routine is written, that is calculated by multiplying the type of the interrupt, that is X, into 4. Okay, so suppose the type of the interrupt it is 2, so 2 into 4, that means 8. So 8 is going to be added to the code segment address, and then the physical address will be obtained. So in this way, the interrupt service routine address, it can be obtained by multiplying the type of the interrupt into 4. Okay. So instruction pointer, it is loaded with the address where the interrupt service routine is written. So now the code segment, that code segment will be loaded with the address where the next instruction is written. So these are the actions which are performed when the INTR interrupt is given to the microprocessor by the peripheral devices. So first the microprocessor, it is going to complete the execution of the current instruction, then all the status of the flags, then a program counter and instruction pointer and the code segment, they are stored in the stack. Okay, then INTA request is generated, acknowledge signal will be given, and then the interrupt, the microprocessor, it is going to receive the type of the interrupt from the interrupt controller. Okay, now the instruction pointer, it is loaded with the interrupt service routine address. So type number, that is the type of the interrupt, will be multiplied with 4. Then code segment will be loaded, and the interrupt flag and trap flag, they are reset to 0. Okay, so these were the hardware interrupts, the non-maskable interrupt, and the interrupt request INTR. Now let us come to the software interrupts of the 8086. So software interrupts are the interrupts which are provided to the microprocessor through the instructions. Means software part is involved of the microprocessor. We are writing the instructions. So that is why these interrupts are known as the software interrupts. So these interrupts, they can be inserted at the desired position into the program. So in the program, wherever we want to interrupt the microprocessor, we can write that particular instruction. So that instruction is going to interrupt the microprocessor. So in this way, interrupts are given. Now these interrupt instructions, they can be used to test the working of the interrupt handlers. In the software interrupts, there comes the various types of interrupts in 8086. First is the INT interrupt. So we can write this instruction INT along with the type number, means by writing here the type of the interrupt. Like if it is type 0, then we will write INT 0. If it is type 1, then we will write INT 1. So INT along with the type number, that is written in the program to provide the software interrupts. So it is the first type of software interrupt. It is a 2-byte instruction. First byte is for the opcode INT, and second byte is for the type number. Now under this group, the 8086 microprocessor, it has 256 interrupts. Okay, so under this category, the 8086, it is having 256 interrupts. Now let us come to the steps or the actions which are taken by the microprocessor when this instruction is written in the program. So in this actions, I have not written the line that the microprocessor, it is going to complete the execution of the current instruction, because this is also an instruction. So first the instruction which is written above this instruction, that will be executed. Then the microprocessor will come to this instruction. So first step will be to that the flag register, it is pushed onto the stack. Then the code segment and the instruction pointer values, they are also stored in the stack. Then the instruction pointer, it is loaded with the address where the interrupt service routine is written. So that address is calculated by multiplying the type of the interrupt, that is the type number, which is provided to the microprocessor by the programmer controller, that is the interrupt controller. It is going to provide the type number, so that type number will be multiplied with 4. Suppose that the type of the interrupt is 2, so 2 will be multiplied with 4, so that will be 8. So the address will be calculated by having this type number multiplied with the 4. Then code segment is also loaded, that is loaded with the address where the next word is located. Okay, and then we have the interrupt flag and trap flag, which are reset to 0. So the steps remains the same, but the changes are that of the interrupt service routine address. So in the case of the INT instruction, interrupt service routine address is obtained by multiplying the type number with the 4. So if we want the starting address for type 0 interrupt, it is 00000H. Okay, so how this address is obtained? Again, the segment address and the offset address, they are combined, so we are getting this complete address for the type 0 interrupt. Now if we want to calculate for type 1, then what we are going to, we are going to multiply it with the 4. The type number will be multiplied with 4. So if we want the address of the type 1 interrupt, then type 1 interrupt will be 1 multiplied with 4, that means 4. So we will have 00004H. For type 2, it is 00002 into 4, that is 8. So it will be 8H. Okay, then we have type 3, type 4, and so on till we have the type 254, because we are having total 256. So up till it we will have the type 0 to type 255. Okay, so type 0 to type 255. So we will have this much interrupts in this INT category. Now, among these interrupts, we have the type 0, type 1, type 2, and type 3, type 4. We have these interrupts which are known as the dedicated interrupts. Then from type 5 to 31, they are reserved for other advanced microprocessors. So these are the reserved interrupts. Then we have from type 32 to type 255. These are available for the hardware or software interrupts. Okay, so this is how from type 0 to type 255, these 256 interrupts, they are divided. From type 0 to type 4, these are the dedicated interrupt pointers, means they are defined for some particular function. Okay, then type 5 to 31, they are reserved for other advanced microprocessors. Type 32 to type 255, they are the hardware and the software interrupts. So if we denote them in the many locations, this is type 4, type 3, type 2, type 1, and type 0. So 0 is having the address 0000. 0H. Then we were having 0000 4H. Then we are having 8. So these are the addresses of these 5 interrupts. Then we have from type 5, which will be, so these interrupts you can see that the difference between the addresses, it is of 4, because every time we are multiplying the type number with 4. So the difference between the memory location will be of 4 bytes. Okay. Now let us see these 5 types of interrupts: type 0, type 1 till type 4. So type 0 interrupt, it represents the division by 0. So whenever the microprocessor, it is performing an operation where a number is divided by 0, so in that situation this interrupt is generated, that is type 0. So whenever such type of division is taking place, then the microprocessor will display a message that is divide 0 on the display screen. Then we have type 1. This represents the single step execution. Single step execution means that whenever microprocessor is executing the instructions, and suppose in between the execution of 2 instructions, it is taking a gap that of single step, so that is known as the type 1 single step execution interrupt. In this case, the trap flag, it has to be set to 1, because trap flag, it is also used for setting this mode single step mode. Okay. Then we have type 2, which is the non-maskable NMI interrupt. When we have studied this NMI interrupt, I have written there that it is the type 2 interrupt. So type 2, it is the non-maskable interrupt. Type 3, it is the breakpoint interrupt. And type 4, it is the overflow interrupt. Okay. So this type 3 interrupt, that is the name is breakpoint interrupt, means whenever the microprocessor, it is executing a program, and the programmer, it wants to take a break in that execution so that it can examine the CPU and the memory. So it is taking a break and the execution. So that type of interrupt is called the type 3 breakpoint interrupt. Now fourth is the conditional interrupt. You can see that when this condition is fulfilled, that overflow flag, it is set, then only that interrupt is generated. So it is the conditional interrupt. So these are the 5 INT, that is the software instructions, software interrupts. Now coming to the priority among these hardware and the software interrupts. So if we study the priority, so these 3 interrupts, that is divide 0 means type 0 interrupt, then INT, any of the type of the interrupt, and INTO. INTO means type 4 interrupt. Type 4 is the overflow interrupt. So here I have written INTO. O is for the overflow. So these 3 interrupts, they have the highest priority. Second comes the NMI, that is the non-maskable interrupt. Third priority comes for the interrupt request, that is INTR. And fourth priority is for the single step. Single step means type 1 interrupt. So in this way, the priority is decided. First, these interrupts, they are having the highest priority, and this is having the lowest priority. Okay. Now, if we come to the performance, that how the hardware and the software interrupts are executed. So if we see for the software interrupts, this is the main program. So when the software interrupts are given to the microprocessor, then this is the execution of that these actions are taking place. This is the main program. The instructions are executed. Suppose at this point the interrupt is provided. So microprocessor, it is going to push the flag register. It is going to clear the interrupt flag and the trap flag. Then it is going to push the code segment and the instruction pointer contents. So all these will be stored in the stack. Then it is going to fetch the interrupt service routine address. It is going to jump at that location. It is going to execute the interrupt service routine. Then it is going to return from this interrupt, that is I return. Then it is going to pop the registers, that is again it is going to get the value of the instruction pointer, code segment and the flags, and again the main program remaining instructions will be executed. So in this way the software interrupts are executed. The following actions takes place. We have summarized it. Okay. Then coming to the hardware interrupts. We were having the 8086 microprocessor. So in 8086, we will have a pin for the NMI, we will have a pin for INTR also, and a pin for INTA bar signal also. So NMI will be given to the microprocessor by some peripheral device. INTR is also given. This NMI, it is an edge triggered input. And this INTR, it is the level triggered input. So whenever this level changes, then this INTR will be generated, and whenever an edge occurs, then the NMI interrupt will be generated. INTR, it is the output from the 8086. Whenever it receives the request, it is going to send the interrupt acknowledge signal to the peripheral devices. So these are the hardware interrupts and these were the software interrupts. So it was the execution, how the software interrupts and the hardware interrupts, they are accessed by the 8086 microprocessor. So in this video, we studied about that what is an interrupt, why there is a need for an interrupt, and what are the types of interrupts in the 8086 microprocessor. So I hope that this topic is clear to you. Thank you.